we will start with the refraction of light due to a prism, or what we call angular deviation due to refraction by a standard kind of triangular prism. So, as all of you have seen in the physics lab, I'm sure, and countless photographs and things, a glass prism is basically something that, you know, the cross section looks like this, or in 3 dimensions, it looks like, in 3 dimensions, it looks like a solid, triangular wedge kind of thing made of glass. That is what we call. So, typically, what we mean by a prism is a solid triangular wedge of transparent glass, and it shows a number of interesting properties, and that is why glass prisms are used in a number of different optical instruments, including spectrometers, periscopes, and things like that. But today we'll study the simple concept of deviation of light, or angular deviation light creates because of the refraction property. Okay. So, standard view of a prism, we will keep the cross-sectional view like this. Okay. And if light is incident like this over here on one face, then it kind of bends towards the normal because it's going from rarer medium air to denser medium glass. And then we'll assume that here it comes out because we're looking at only angular deviation or refraction. We're not looking at total internal reflection. But there can be a situation where it bends so much here that the second incidence makes it critical to total internal reflection. So that's a different situation. So we'll discuss about that also. But here we're assuming the second incidence is also resulting in refraction. And ultimately the ray of light is emerging out like this. So when this kind of situation happens, this is called the incident ray. This is called the emergent ray. And the angle between the two faces which are doing the refraction, that one becomes the important angle, and we call that the angle of the prism. So E is now called the angle of the prism. You realize something, that the other two angles don't matter here, because even if I were to break this prism and make it a different shape over here, whether this prism was like this over here, or it was spherical surface, or at some other angle, it doesn't matter. It does not affect the geometry of this image. So that is why the only angle, the only geometrical factor of the prism that becomes important is the angle between the two faces that are doing the refraction. Okay, so angle of the prism is the angle between the two refracting surfaces. Okay. Now further, here if I draw normal at the point of incidence like this, this is, let's say, a normal. So this is my angle of incidence, and this is my angle of refraction. And since there are two refractions happening, so we'll call this R1. And if I draw another normal now at this point, so that looks something like this, let's say. So this other normal here, this becomes the angle of incidence. Okay. So I just magnify this a bit because the diagram is. Okay. So let's look at this more carefully now. Okay. So this angle is R2 and this angle is E. I mean, this is the general this thing that we use, terminology that we use. Okay. And let us also label all these points, because so the point of incidence is this point over here, so let's say that is P. The point of emergence is this point, so let's label that as Q, and let's also label this point as R. And this vertex of the prism, we'll just label it as E. Now the main thing that we're interested in is the angular deviation. So in this diagram, if you see what is the angular deviation, for that you produce the incident ray forward. So that becomes like this when you produce it forward. So this is your incident ray produced forward, and you produce a refracted ray backwards. So that is this. Okay. So the angle made between these two, that becomes the angular deviation. So incident ray produced forward and emergent ray produced backwards. इनके भी जो angle बन रहा है, that is the angle by which this has deviated. So this is delta. That is called the angular deviation. So you can see that the ray of light was incident like this, but then it met the prism and it came out from this side like this. So it got deviated like this by delta. So that is the delta. That is the angular deviation. Okay. And let us also in our diagram label this point here as something. So let's label it as S. Okay. So the main thing now for us is to come up with the geometrical solution involving optics, of course. We have to find the value of the angular deviation delta, given that we know the angle of the prism, we know the refractive index of the glass of the prism. This is and we also know the angle of incidence. So given these three quantities, we have to find a geometrical solution, which of course involves the refraction also. How to find the deviation? The terminology here is I is called the angle of incidence and E is called the angle of emergence. And of course, you have two refractions involved. So the equations start with the Snell's law applications. So if you look at the Snell's law applications for air to glass at that point P which we had labeled, you will have sine I equal to mu sine R1. Okay, so that's my first equation. Let's just go back to the diagram and understand this. So at the point of incidence P, you see we have it's going from air to glass, and I is the incident angle, R1 is the angle of refraction. Now the next refraction is happening at this point here, which is Q. So उसपे क्या हो रहा है? Glass to air. Okay, so second refraction, glass to air, that is happening at the point of incidence which is Q. So वहाँ पे क्या है? The angle of incidence is actually R2. So mu sine R2 is this, and that is going into air with an angle of emergence, or which will actually be the angle of refraction for that, and that will become this. So this becomes my second equation. Okay. But as you can see that these equations are obviously not enough, because we have R1, R2, E and I, four unknowns, or at least three unknowns, R1, R2 and E. And we have two equations. So that is where the geometrical solution now comes in. Okay. So now we have to look at the geometry of the prism. Okay. And for that, you start by looking at this, just follow my cursor. You start by looking at this quadrilateral. You see the quadrilateral I'm pointing at. Okay. PRQA. This is a quadrilateral. But उसमें क्या होगा? That if I label this angle here as theta, you can see now this quadrilateral PAQR is such that two of the angles of opposite sides are 90 degrees. Because these black dotted lines are normals. Some of the other two angles has also got to be 180, because some of four angles have to be 360. So now we start looking at the geometrical relations. In the geometry, we start by looking at the quadrilateral in this, we apply the concept that sum of angles, interior angles, has to be 360. Okay. But in this, you can see that angle APR is equal to angle AQR is equal to 90 degrees. Okay, because so just go back to the figure and you can see that angle APR, this one, and angle AQR, this one, these are both 90 degrees because these two dotted lines, PR and QR, they are nothing but normals to these two interfaces. Okay? So they are each 90 degrees. Okay? So therefore, angle PAQ plus angle PRQ has got to be 180 degrees. So angle PAQ is nothing but angle of the prism. Okay? So you can see angle PAQ is nothing but A in degrees, which is angle of the prism. And we have taken in that figure angle PRQ as theta. So A plus theta is 180 degrees. Okay, so this becomes another important equation from here. So basically what we are saying in this is very simple. ये वाला angle और ये वाला angle 90 for this quadrilateral. These two angles are 90. So the sum of this angle theta and this angle E has to be 180 degrees. So as simple as that. So this angle theta is becoming 180 minus A. Now you also look at this triangle PQR. In this R1 plus R2 plus theta has to be 180. So that means basically what is theta? It is R1 plus R2. So next thing, this is what you're getting from the quadrilateral. Okay, now next thing you look at the triangle PQR. In that R1 plus R2 plus theta has to be equal to 180 degrees. So this result you put together with this result now. So the combination of these two now gives you one very important relation which you will have to keep in mind while solving prism problems. Okay. So R1 plus R2, the sum of the two interior angles in the refraction process, that is always equal to the angle of the prism. So this becomes our third significant equation. So I will just leave you to this to note down this part first. So first just make a note of this diagram and the Snell's law equations. Then you can note down the geometrical relations below. Okay. So remember what is happening is we are solving for delta and we are given the values of A, mu and the angle of incidence. So now for us what all is unknown? Delta is unknown, R1 is unknown, R2 is unknown and angle of emergence is unknown. So we need a total of 4 equations. So 2 equations have come from Snell's law and so far we have got one equation by applying the geometrical conditions and that is R1 plus R2 is equal to E. Now one more equation will come from another geometrical consideration and that's it. From that we'll be able to find out the angle of deviation which we are trying to get in the first place. Okay, so just make a note up to the Snell's law part first, then we'll come to the geometrical part. And make sure you understand the labeling in the figure properly. Okay, so I'll show you the next part also, but first let me just once again magnify the diagram also for you so that So make sure you label your figure correctly so that you can understand the geometrical part now. Okay, so hope you are following all this till now. All right, so now let's come to the geometrical equations that you get in that, which is this. Okay. So ultimately, this is the equation you have to remember. You don't have to remember this derivation while solving problems, but it's critical that you understand where this equation comes from, because every time we are doing a numerical problem involving a prism, we'll have to take these equations into account. So finally, this equation that R1 plus R2 is equal to E, that becomes important. Okay, people, so hope this is clear. So now let's come to the final equation. So for the final equation now, we will consider another geometrical thing in this. We'll consider this triangle now. So we'll be considering this smaller triangle. This one, PQS, where delta is the exterior angle. So for this triangle, we first of all also label these interior angles. So my diagram is going to be a little challenging for me, but let me try anyway. So this angle, let us say, is delta 1, and this angle here is, let's say, delta 2. Okay. So now you can see that delta 1 is actually the deviation of the first ray. So it is I minus R1. So that delta 1 over there is actually I minus R1. In the second one, you can see delta 2 is the deviation for the second refraction. So that delta 2 is actually equal to E minus R2. Okay. And in terms of proper labeling, this delta 1 I'm talking about is actually this angle, angle SPR. Okay. And this delta 2 I'm talking about is actually this angle, angle SQR. Okay. That is equal to delta 2, which is this. Okay. So now you can see that for that triangle, for this small triangle here, PQS, delta exterior angle and the interior opposite angles are delta 1 and delta 2. So the sum of delta 1 and delta 2 should be equal to delta. And that is finally what we're looking for, which is the exterior, which is the deviation. Okay. So let's put this as our final equation now. Okay. And with that, so the final consideration is triangle PQS. So in that triangle, we can see that delta 1 plus delta 2 is delta. Okay. So that makes it I minus R1 plus E minus R2 is the net angular deviation. Okay. And now you put this over here and we get the relation that the angular deviation therefore becomes I plus E minus R1 plus R2. So that becomes E. So this becomes our fourth and final equation that we require to solve the prism problem. So we get two equations from Snell's law that you don't need to memorize, you just understand. And third equation you get R1 plus R2 is equal to E, and the final equation is delta is equal to I plus E minus E. So these are the four equations that we use to solve any numerical problem involving deviation due to prism. So just note this part down here, and then I'll take you back to the diagram so that you can understand it once again. Just note this part down. Yes, Austin, that is correct. Angle of deviation is not that correct. Okay, so just taking you to the diagram above once more to fully understand how this is working out. Okay, so let us see a problem and understand how these equations are used. So basically, given a typical problem, given angle of the prism, the refractive index, and the angle of incidence, we want to find out delta. So how do we proceed? So first step is we use this relation that sine I is equal to mu sine R1 for the first refraction. So from this we find out R1. Then next step what we do is we use a relation R1 plus R2 is equal to the angle of the prism. So we substitute this here. So then that gives us R2. Then third step we again apply Snell's law. So mu sine R2 is equal to sine E. So this value of R2 that we got we substitute here, and that now gives us the angle of emergence. And once we have the angle of emergence, final step, we find out the angle of deviation using that formula where it is I plus E minus E. So we substitute the angle of emergence in this and we got this. Okay. So this is a sequence of steps that we follow. So let's take an example. Let me say in my example that this angle is 60 degrees and the incidence is happening. Let us say that this angle is 45 degrees. So we want to trace the ray diagram. So in that level I, R1, R2, E, etc. And finally find the angular deviation delta, given that the refractive index of the glass, that is standard value 1.5. Okay. Now this is an arbitrary question, so it will require, we'll most probably come across angles which are unknown for us, so we'll use a scientific calculator. Okay. So let's start with the first thing. You can see that the incidence which is happening here, if I draw this normal, you can see this is my angle of incidence I. So I will become how much over here? 45 degrees. Because this other angle is also given as 45. So now let me find my R1 from this. So if this ray has now bent a little bit towards the normal, let's say, so it's something like this. So in this diagram, as usual, my R1 is this angle. So R1 कितना हो जाएगा? So sin I is equal to mu sin R1. So R1 will become sine inverse of 1 by root 2 divided by 3 by 2. Okay. So okay, R1 is approximately sine inverse of 2 by 3 into 1 by root 2. So R1 will be approximately sine inverse of, will be equal to, now I'll do the approximation. Two by 3 is approximately 0.67 and 1 by root 2 is approximately 0.7. Okay. So this is where I'm going to use a calculator now. Okay. So you can also do that. Or in an exam, the values will be such that it's easy to calculate, or some values will be given to you. So anyway, 2 by 3 so when I calculate this thing, it will come close to about 28.2 degrees. Okay, this is what I'm getting according to my scientific calculator. So this is the next step. Okay. So using the angle of incidence, I've done step 1. This was my step 1. I calculated the angle of refraction. So just make a note of this first. Right. So now next I can see that the angle of the prism, so from here I'm going here, step 2, angle of the prism was 60 degrees because that was the angle given between the two refracting surfaces. This. So this second one over here, the second refraction over here, this angle we can calculate by the simple geometrical fact that R1 plus R2 is always equal to E. And finally then we'll use Snell's law once again to find the angle of emergence. And then finally we can see that the angle made between the incident ray produced forward and the refracted ray produced backwards, this angle will be our delta. So this is a fairly simple step now. R1 plus R2 is equal to E. Substitute this value and R2 comes out to be 60 minus 28.2, so that is 31.8 or nearly 32 degrees. So what this comes. Now again apply that in Snell's law. So mu sine R2 is equal to sine of emergence. So E will become sine inverse of 1.5 into sine 31.8. So again, I'll use a scientific calculator to work this out. But actually, you can see this will be very close to sine 30, because 31.8 is very close to that. So it's almost 1.5 into half, so that is 0.75. So sine inverse of 0.75 will also do, but I'm doing an exact calculation here. So 31.8 plus sine is around 0.53, and multiply that with 1.5, so that gives us around 0.79. Okay. And then I'm taking sine inverse of that, so that is giving me about 52.2 degrees. So that was my fourth and final step. Okay, so this was my step 4. This is giving me the angle of emergence as approximately 52.2 degrees. Or rather, this was my step 3. And the final step 4 is the angular deviation. So that is I plus E minus E. So here that becomes 45 plus 52.2 minus 60. Okay, so that becomes about 37 degrees. That is our net deviation. Okay. So this becomes our findings. So this is the sequence of steps that we follow to calculate any deviation. So we can see that this ray carried forward and this ray emerging out now, this deviation is coming out approximately 37.2. Okay. So I'm just minimizing this so you can go through all the steps. So this one question actually captures everything that you require. Okay. And it sees how you're making use of these formulae. That R1 plus R2 is equal to angle of the prism, and the net deviation is I plus E minus E. And apart from that, you have Snell's law and the two cases. Okay. That's all you need to remember about solving any prism related problem. Of course, there are some other things we'll see, like the special condition for minimum deviation, special condition for maximum deviation, range of deviation, things like that. Okay, so just taking you to the last part of the calculation here. Okay, people, so hope this is clear. The full calculation. Now, the next thing we'll understand here is the principle of reversibility applied to light. So we apply reversibility principle. So suppose we are having a situation where in one case our angle of incidence something here such that so something like this is happening where this angle is actually some alpha, the same value, and this angle is some beta. So if I is equal to alpha and emergence is equal to beta, okay, and we are getting deviation is equal to therefore alpha plus beta minus E, where E is this angle. Now apply the principle of reversibility on this. So if this ray of light had been incident in, let us say, this manner, then it would have come out like this only, because all these would have just, they would have just reversed themselves. So now if I have a situation where the actual incidence is happening from the same side, but at an angle of incidence, which is this one. Okay, so now think of it like a mirror image of this diagram. So this is actually happening now like this. Bending it towards the normal, again, something like this. So in this diagram now, suppose whatever this angle was, this is now this angle. Then automatically what will happen is the angle of emergence will become that angle because of the reversibility principle. So if in this case I is equal to beta, then automatically for the same prism with the same angle of the prism, the same refractive index, E will become equal to alpha, but the deviation will be same as that is. So this is the reversibility principle. So this basically tells me that if I am looking at the relationship between the angular deviation versus the angle of incidence, so looking at delta versus angle of incidence, then any particular value of delta occurs for two different angles of incidence. So for example, that case that we just saw, where angle of the prism was 60 degrees and for incidence equal to 45 degrees, we got emergence equal to 37.2 degrees. And that gave us a deviation of, oh sorry, we got emergence of 52 point, whatever that was. Yeah, it was 52.2 degrees, which gave us an emergence of 37.2 degrees. Mu equal to 3 by 2. In this case that we just done. So that point is, let's say, over here. So this delta is, suppose in that example, this delta is 37.2. So there's one data point where it will happen for an angle of incidence equal to 45 degrees. Okay. But it will also happen if I take angle of incidence equal to 52.2 degrees, then my angle of emergence will come out to be 45 degrees. Okay. And my deviation will be same, 37.2. So that means it will also happen at another data point over here. So like that. So if we start plotting, we see that the graph, it's a non-linear kind of graph like this, okay, where at a particular angle of incidence, which we can call I0, which becomes a unique angle. the deviation becomes a unique value, which is minimum. And also, at a particular angle, the deviation will also become maximum. And the difference between this and this will be the range of deviation. This is the range of deviation that we can get. Okay. So what we'll see is that for I1 equal to alpha, E1 is equal to beta, we get delta equal to alpha plus beta minus E. For I2 equal to beta, E2 becomes alpha and we get the same deviation. Alpha plus beta minus E. Okay. So that means for each value of delta, generally there are two possible points. At the minimum deviation condition. So at that condition, what happens is I1 is equal to I2 is equal to what we are calling I1. So that means alpha is equal to beta, which is equal to I0. So that means angle of incidence is equal to angle of emergence is equal to that value of I0 for delta equal to this. So this is what we call the minimum deviation condition. That when the angle of incidence is a value such that the angle of emergence becomes equal to the angle of incidence, then the corresponding value, okay, then delta becomes delta. Okay, and we'll develop a formula for this also. Okay. But first of all, note down the graph and understand the trend over here, the pattern, so that this will become more clear. So this is deviation versus angle of incidence. You see it's a pattern like this. Like that, we'll discuss about maximum deviation also. But first, understand the minimum deviation condition from this. Okay, people, so minimum deviation condition becomes like this. So now let's mathematically develop a formula. Okay, so let us look at this minimum deviation condition more carefully. Oh, sorry. I think you people were noting down this part. So let me just right. So let's now understand the minimum deviation condition in more detail. So basically, from the graph pattern, you understand that minimum deviation happens at a symmetrical kind of situation where the angle of incidence has to be unique. So that means it has to be reversible from the same side with a unique angle. That means the angle at both the sides have to be same. That is, I has to be equal to E. That's where the symmetry thing comes. So just draw this so that I'll get more place here. So ऐसा symmetric होना चाहिए, then the deviation is minimum. Whereas the moment it's asymmetrical, that is, the angle of incidence is not equal to the angle of emergence, your deviation will be more than the minimum deviation. So for this angle to be the minimum deviation, what you want is that we are in the situation where this angle has to be equal to this angle. And therefore, what will also happen is that this angle will be equal to this angle. So, delta अगर minimum value है, it implies that I is equal to E, which is equal to that value I naught which we assume. Okay. So that also means that R1 is equal to R2, equal to R. Okay. So first of all, we have R1 plus R2 is equal to angle of the prism. So that tells me that R is equal to A by 2. So now that tells me that R1 equal to R is actually equal to E by 2. So now this tells me that sine I naught is equal to mu sine E by 2 using Snell's law, that sine I is equal to mu sine R1, this one. So I get this. This tells me that I naught is equal to sine inverse of mu sine E by 2. And that gives me the formula of the minimum deviation. Delta minimum becomes, so delta in general was I plus E minus E. That was the other formula. So we use that over here. So this becomes 2 times I naught minus E, or becomes 2 times sine inverse of mu sine E by 2 minus E. So this you can think of as a formula so-called. But the thing is, you don't need to memorize the formula. You just need to keep in mind the concept that when you are in the minimum deviation condition, what is happening is this thing, that because your I is equal to E, so your R1 is equal to R2, so that becomes E by 2. So next, once you know your R is E by 2, you know that delta is this. So this is the calculate the minimum. Okay. So hope you people have understood this. There was a bit of video lag again, but hopefully the audio is fine. So now let us apply this in that particular question also. So as you're noting this now, we'll also, as an example, we will find the minimum deviation angle and the deviation is the minimum deviation. For that data, E was 60 degrees and mu was 1.5. So let's see that particular example. So if angle of the prism was 60 degrees for I equal to E, R1 is equal to R2 is equal to A by 2. So that becomes 30 degrees. Okay. So now sine I becomes mu sine R1. So here sine I0 becomes mu sine A by 2. So I0 should be sine inverse of mu, which was 1.5 into sine of 30 degrees. So sine inverse 3 by 2 into half, or sine inverse 0.75. Okay. So if I do a calculation of, if I use the scientific calculator or a log table, whatever, to find this out. So 0.75 ka sine inverse will come out to be about 48.6 degrees. So this is the angle at which we'll get the minimum deviation condition. And the minimum deviation value itself will be 2 times I0 minus E. So in this case, it will come out to be double of this minus 60 degrees. It will come out to be about 37.1 degrees. So if we just doing this, looking at this graph, see the deviation versus angle of incidence. Like this, it would be where this data point would be for I naught equal to about 48 point whatever that was, 48.6 degrees, and minimum deviation equal to about 37.1 degrees. Okay. Whereas we had seen the other data points earlier, they were these angles were some 45 degrees and 52.2 degrees or something, which was giving us slightly greater value of delta. It was giving us 37.2. So you can see that actually they are very close. But anyway, we take some other angles like 30 and something else, you'll see deviation keeps going like this. Okay. So this is the minimum deviation condition, and this is how we calculate it practically. And we'll also see the maximum deviation condition next. But okay, let's now understand the maximum deviation condition. So maximum deviation will happen in a situation where, so if you are having one incident ray, so let's say coming out like this, so we're getting a certain amount of deviation. Now in this diagram, you can see that it's such that the particular angle of incidence that I have selected, it's corresponding to a situation where the angle of emergence is more. So I is greater than E here. So it's in which part of the graph? It's somewhere here, because that corresponding I has the corresponding E over here, reversibility. So it's in this point. Okay. So from here, if I now reduce the angle of incidence to some I prime, what will happen is my deviation will increase and my angle of emergence will also increase. So if I is switched to I prime, which is I minus some delta I, then my angle of emergence will increase to E prime, which will be E plus delta I, and overall my deviation will increase. And deviation increases. Now the thing is, till when can I go on decreasing? Okay, so I can go on decreasing this angle of incidence till this reaches a situation where it's just about grazing the surface. Then if I decrease I further, what will happen? Yahan pe it will do DIR. Okay, so if we come to a limiting kind of situation where it's just about ready to do total internal reflection. So I have made the angle of incidence lesser than this, something like this. And now this is what is happening. This is just about coming on. This will correspond to the maximum deviation condition. So this angle of incidence is some special value for which the angle of emergence over here is tending to 90 degrees. So that will correspond to this maximum deviation point. This will be my delta maximum, and that corresponding value of I is some I double prime, let's say. So that's so this incident ray is having a grazing emergence. E is tending to become 90 degrees. That is the solution. So for maximum deviation, the value of I is such that the emergent ray grazes the surface. That means the angle of emergence tends to become 90 degrees. So now again, looking at that sequence of events, you'll understand that यहाँ पे अगर grazing हो रहा है, that means यहाँ पे जो angle of incidence है, that is a critical angle. So we'll now make use of that to find out what should be the angle of incidence on this side. So if the angle of emergence is 90 degrees, then this angle will become critical angle. So R2 becomes critical angle, which is nothing but sine inverse of 1 by mu for that particular glass piece, whatever the mu is. So then this R1 becomes E minus critical angle, because R1 plus R2, remember, was equal to E. So making use of that, and therefore this, whatever this angle of, let's call this minimum. So this I minimum comes as sine inverse of mu into sine of this R1, which is nothing but A minus critical angle. So this is how we get this. So we get this section of the graph where you are having the possible minimum possible angle, which is giving you refraction. your emergence is working out to be 90 degrees, and that is giving you your maximum deviation. So this situation corresponds to this max over. So just make a note of this, people, and you'll also see this with an example. All right, so now of course remember here reversibility again applies. So also by reversibility, if angle of incidence is tending to 90 degrees, that is we have grazing incidence, then angle of emergence will be equal to whatever this I mean was over here. That is sine inverse of mu sine E minus critical angle, and delta becomes delta maximum. So delta maximum occurs in two conditions. When I is equal to I minimum, emergence is 90 degrees, or when incident angle is 90 degrees or grazing incidence, so the emergence becomes that minimum angle. But in both cases, you get the maximum deviation. So again, let's just calculate for that value. So for example, if E is 60 degrees and mu is equal to 3 by 2 or 1.5, so you can see that you want to calculate what this maximum deviation is. So you can see that emergence is 90 degrees, that means R2 is the critical angle. So that will become sine inverse of 2 by 3, which if we calculate is approximately, so 2 by 3 is 0.67. If I do sine inverse of that, I get about 41.8 degrees. So that means R1, which will be E minus R2, will be approximately 18.2 degrees. So from that we will see that I minimum will be such that sine of I minimum is equal to mu sine R1. So that is 1.5 times sine 18.2. So this becomes lost somewhere. Yeah. So this I minimum. So this becomes about 0.47 approximately. So I minimum becomes equal to sine inverse of 0.47, which will be very close to 30 degrees. So this becomes approximately 27.9 degrees. Okay. That is my I minimum. So my maximum deviation is equal to this I minimum plus 90 degrees minus E. Because remember, delta in general was I plus E minus E. Whereas in this case, E is 90 degrees and I is that I minimum. So in this case, this will become about 90 minus 60, so 30 plus this will become 57.9 degrees. So that is minus. Okay, so now concluding for this particular example, everything that we've seen so far, you realize that the range of deviation is now something like this. This. So this was about 57 point something we just saw. I minimum was 28 point something, 27.9 and 57.9. So nearly 28 degrees, 58 degrees. This was nearly 28 degrees. And where we saw the minimum deviation was approximately 37 degrees for 48.6 degrees. So this is the complete range of deviation which you can see for this particular graph. So you can understand here that if you keep the angle of incidence at, for example, that 48.6, you are starting from this position. From there if you start decreasing the angle of deviation, so the graph goes in this direction. So your angle of incidence is decreasing, but your angle of emergence is increasing till you reach the grazing condition. In the grazing condition, you are having grazing emergence. So E is 90 and angle of incidence is 28 degrees. On the other hand, from 48.6, if you start increasing the angle of incidence, your angle of emergence starts decreasing. But up to where you can increase the angle of incidence, till you have grazing incidence, that is your incidence is like this. Your incidence only is, the light is just about incident grazing. So it refracts in at critical angle and it comes out at this. This is E is equal to 90 degrees. So R1 becomes critical angle. R2 becomes A minus critical angle. And then this angle of emergence here So this angle of incidence. Angle of emergence becomes that sine inverse mu sine r2, where you substitute this. So that becomes this case where your angle of incidence is 90 degrees. So just a quick note for this. Okay, so people, this is like the complete analysis of any prism. Range of deviation, minimum deviation, maximum deviation, condition of minimum and maximum deviation. But basically, you don't need to memorize so many different formulas. If you just, basic things about the prism that you keep in mind are these things, that R1 plus R2 is equal to E, and that the net deviation becomes I plus E minus E, along with, of course, Snell's law. So if you keep this in mind, and then you keep in mind the condition for minimum deviation, that is that I is equal to E and R1 is equal to R2, which becomes E by 2. So then just put this in Snell's law and we get along with the first two equations. And the condition for maximum deviation is either that your emergence is grazing, so your R2 is critical angle, so your R1 becomes E minus critical angle, or that your incidence was grazing, so your R1 becomes critical angle, So your R2 becomes E minus IC. Just if you just remember this concept, okay, that this happens or this happens, and in the case of this, this happens and this happens, then it's easy to remember these two things. So this I mean should be more than enough to be able to solve any problem on the spot. That is about the prism. Now we also have a situation where we look at the approximation for thin prisms. So by thin prism we mean that the angle of the prism is a very small angle. Typically it should be less than about 5 degrees, such that sine A can be approximated as E in radians, of course. Okay, so that we can do that small angle approximation. So now what happens in the case of a very thin prism is that there is hardly any deviation of light. And that we'll understand like this, because there is very, very little deviation. That happens. Because the angle of the prism is very small. Because, just consider what if the angle had been 0. So you're talking about a very narrow slab of glass like this. So what would happen in the case of light incident on a very narrow slab of glass like this? The angular deviation would in fact be 0. This would come out such that this comes out parallel. There's a bit of linear displacement, but there is no angular displacement. A bit of linear deviation, but comes out parallel. So delta would be 0 here if A is 0. So delta is also accordingly very small. Okay. So because delta is very small, delta itself is very small for any angle of incidence. So that means the range of deviation is also very small. So delta can be approximated as delta minimum. And for delta minimum, we have that situation that delta minimum is 2 times I naught minus E, where we have sine I naught is equal to mu sine E by 2. Because for the minimum deviation condition, we have R1 equal to R2 equal to E by 2. So in this equation now you can see that we can write sine I naught as approximately mu into E by 2. Okay, because E by 2 is a small angle. Okay. So now what is happening? I naught is equal to sine inverse of mu A by 2. Okay. Now mu A by 2 is also a very small value. Okay. So mu A by 2 will be approximately equal to sine inverse mu A by 2. Okay. This is like basically saying that sine theta is approximately equal to theta. That means saying that theta is approximately equal to sine inverse. It's one and the same. Okay. So I naught becomes approximately equal to mu E by 2. So now substituting this back over here, that delta minimum becomes approximately equal to mu minus 1 into E. So because the range of deviation itself is very short, because the range of deviation is negligible. Okay, that means delta max is equal to delta minimum is equal to mu minus 1 into E. So for any angle of incidence, for any angle of incidence, the deviation is approximately equal to mu minus 1 into E. So this is the thin prism approximation method. So anytime we come across a thin prism with the angle of the prism something like 2 degrees or 4 degrees or something very small like that, we can directly write the deviation, the angular deviation like this. That's the final part, just make a note of this. Okay, so basically anytime you have a thin prism, any angle at which light is incident, it will just bend by that much. So, for example, we have a thin prism of angle of the prism, let's say 4 degrees. So a ray of light, suppose it's incident horizontally like this over here. So it will have to emerge out at just something like a 2-degree deviation. This deviation, this delta, will be mu minus 1 into A. So if we take mu as the standard value, 1.5 for glass, it will be 0.5 into 4 degrees. So it will be a 2-degree deviation. So this is how we deal with any thin prism situation. So that completes the analysis for prisms. Now, next we will move on to optical instruments, which, by the way, is a topic only for JEE mains. So optical instruments consist of combination of lenses. So So that way it is not anything new from what we have learned. Just the lens formula is required. But the specific formula that we develop for magnification created by a microscope or telescope or things like that, those specific formulae are only for JEE Mains. So for JEE Advanced, we still have a couple of things to do, which we'll do in the next lecture when that RTPS2 batch joins us. That will be the combination of thin lenses in contact and lens and mirror in contact. So that will be one very important lecture which we'll see next time in terms of problem solving at JEE Advanced level also. But in the meantime, let's complete this portion, which those people have done early in the morning. So optical instruments, the first thing we need to understand is angular size of an object for a given viewer. And from that, the concept of angular magnification. Which is produced by using an instrument to see it. So let's understand these two concepts. So the concept of angular size, or you can also call it angular width, something like this, that if you have an object, let's say AB, an object, and the observer's eye is located over here. So this is the eye of the viewer or the observer. Okay. Then the total angle subtended by that object, this angle, that theta is called the angular size. And you'll realize that angular size has a great deal to do with how we perceive the size of an object. Okay? Same reason why, if there is a person standing in front of you, okay, but there's also, let's say, a tree behind you, which you can understand is of larger size, but you are viewing from somewhere here. Your eye is located over here. And it might almost appear as if this angle is the same. So you perceive this part of his body to be the same size as the entire tree. As you know, the size of the tree is more. So that optical illusion of objects being further away appearing to be smaller in size, and objects being closer appearing to be larger in size. Okay? Or you can see that if a person was initially present here and then he moves to this position here, then for an observer over here, the angular size suddenly changes. It goes from a smaller value to a larger value by the time it's coming here. Okay. Or another way to perceive this is, for example, you have an observer over here and there's an object A that is moving at a comparatively slower speed, and there's an object B much further away but moving at a much larger speed. Now this was at t equal to z, and you can see that VB is greater than V as I've drawn the vector. But now, suppose after some time, A has reached here to A prime, whereas B has actually covered a larger distance but reached somewhere here, B prime. So you can see B's displacement is more than A's. But what will happen is A's angular displacement is this much. This is delta theta for A. Whereas B's angular displacement is going to be only this much. Okay. So if delta theta B becomes less than delta theta A, so then B appears slower than A. Okay. So that is why, for example, a distant aeroplane appears slower compared to a person running near you, because the angular shift becomes more, so it appears like it's covered more ground, but actually it is not. So this all has to do with the perception of distance and geometrical quantities like that, which is more to do with angular position, angular size, and angular displacement rather than linear size and linear displacement. Okay, so just make a note of this, then we'll understand the concept of angular magnification. Right, so this is the concept of angular size. Okay, now if we are talking about angular size of a very small size object, for example, a printed alphabet, or a dust particle, hardly you can see it. Printed alphabet, of course, you can see clearly, but so what happens in that case is, if this is the object and this is where the eye is located, then the object's height is suppose h. So the height AB, suppose h, and the distance from the eye is x. Then by small angle approximation, this angle theta becomes approximately tan theta. So theta becomes h by x. So that means the closer we bring it, the larger we can see it, which is obvious. Okay. So by minimizing x, we can maximize theta. But there is a limit to this, and that limit is basically what? That the minimum distance at which we can sharply focus the image of an object in our retina is limited by our eye lenses. You can say physiological makeup, okay? And capital D is called the least distance of distinct vision. which is basically the minimum distance at which the eye lens can adjust to focus at the retina or create a focused image at the retina. So basically, therefore, for x less than b, the image will not be sharp. It will be blurry. Okay. So for normal adults, d is statistically an approximate of 25 centimeters. Okay, so we are limited by our physiology of the eye lens and the entire optical system that we have, that we cannot bring an object closer than about 25 centimeters. Okay. So that is why we say that the maximum angular magnification for a small size object of h without any optical instrument is given by this. So this is the maximum angular size for unaided viewing of an object. Unaided means no instrument. You're not viewing through any instrument. Okay. So for example, if you're looking at the angular size of something which is half a millimeter in width, so that will be half a millimeter divided by 25 centimeters. Or if you're looking at something like something at the cellular level, you see the angular size is so small for that cellular size, which will be typically in some microns or something, divided by 25 centimeters. That angle is so small that you can't really perceive it. It becomes beyond your the human eye's capability of perceiving that object. Okay. So that is where optical instrument comes in, and we try to increase the angular size by using an optical instrument. So just make a note of this concept first. The concept of least distance of distinct vision. Okay, so got it, people. So now, if using an optical instrument, the angular size becomes theta, then The ratio of theta is to theta naught, where theta naught was that reference value of angular size at the least distance point. That is called angular magnification. So this is called angular magnification. It is the ratio of angular size as seen through an optical instrument with respect to that angular size without any aid of optical instrument when it is kept at the near point of the eye. So once you understand this concept, it becomes easy to understand how we develop the formulae for angular magnification for all the different types of instruments. So now let's talk about some of the type of instruments. So the most basic one is the one which explains the whole concept actually. And that is the handheld microscope or handheld lens, what we also call simply a magnifying glass. So this is actually nothing but a convex lens of focal length f, such that typically f is less than the least distance of distinction. So what we do in this case is got this, and the eye is kept more or less near the pole. Now on this side, if that object AB is kept at some distance x, where the focal position is somewhere here, so definitely x is less than focal length. So it will produce which type of? It will produce a virtual upright and magnified image. So what will happen here is that the rays of light from this such that we produce this back. Something like this will happen. So it will produce a virtual magnified and upright image, let's say E prime B prime, which is let's say at a distance of y. So what happens is the observer on this side, his eye, it does not perceive this object AB, it perceives the image of AB, which is A prime B prime, and which is at a distance y. So the viewer's eye perceives the image E prime B prime at distance y behind the lens. So therefore, as long as y is less than equal to capital D, he or she can see a sharp image of that object. But now what is happening? You can see the angular width of the image that is seen. A prime B prime ka angular width kitna hai? That is this theta. It is the same as this theta. So ultimately, this ray passing through the pole is undeviated. The ray passing through the pole is undeviated. Okay? So this image that he sees perceives the image A prime B prime of angular size theta. Now in the diagram, if you see again, you see theta is equal to h prime by y, which is actually equal to h by x, where h prime would be the size of this image. This is suppose h prime, and the object was of the size h. So both of them are the same. Okay. So therefore, the angular magnification achieved by the instrument is nothing but theta upon theta naught. So this is h by x divided by h by capital D. So the angular magnification achieved is equal to d by x. Okay. And remember, in general, we are keeping x less than equal to focal length, and the focal length of the lens was less than capital D. So it's a magnification. So m theta is greater than 1. So it's an angular magnification. Okay. Just make a note of this, and then we'll understand the different kind of position that which we can achieve. Different types of magnification, or the range of magnification that we can achieve. So whenever we are talking about magnification achieved by an optical instrument, whether it's a microscope or a simple handheld lens or whatever, remember we are not talking about linear magnification. We are not talking about h prime upon h, which is image distance upon object distance. We are talking about angular magnification, which is theta upon theta naught. So that is the angular size of the image as seen by the observer with respect to, if there had been no instrument, then what is the maximum angular size you can see? That is theta naught. So that is nothing but h by capital D. So it is that kind of magnification that we talk about in all optical instruments. Now the other thing is, you just make sure you note this down first, then we'll come back to this. Now going back to the working of the lens here, in terms of lens formula, you'll see we use 1 by v minus 1 by u is equal to 1 by f with sign convention. We get 1 by minus y. So in my diagram, the image is at y behind the lens. Okay. Minus 1 by u is equal to 1 by f. So we get this relation that 1 by y is equal to 1 by x minus 1 by f, or y is equal to xf upon f minus x. Or if we invert this, we also get that x is equal to yf upon f plus y. Okay. So in this you can see that those relations that we wrote there, that 1 upon x minus 1 upon y becomes 1 by f. On substituting u as minus x and v as minus y, we can see that x decreasing from focal length towards 0, y also decreases from infinity to 0. Okay. But remember, for proper view, that is a sharp view, okay, y should be less than equal to capital D. Because remember, your viewer is observing the image A prime, B prime, and that should not come closer than the near point of his eye. Okay? So that becomes a limit for us. Okay? So that's how we get the range of magnification. Range of magnification we get like this, that on the one hand, we have if x is equal to focal length, just about equal to, slightly less than, slightly less, but almost equal to, then y is infinity means very large. In this case, what we get is a very distant but magnified image, and because it's very distant, the eye is comfortable. You don't really have to squint. Your eyelash doesn't have to be bulged. So it's in a comfortable kind of situation. So that is why this is called the normal adjustment position for the lens. When we put x as just about less than focal length, so our y becomes a very large value, and at that point of time we get the angular magnification as b by f. Because remember, the general formula for angular magnification was theta by theta naught was d by x. Now here we put x equal to f. So this is the magnification. So this is the condition where we get actually minimum magnification. But the eye is comfortable. Because the image that you're seeing is not very close to you. So the eye doesn't have to bulge extra to sharpen the image. Let's start from this analysis here. So this is from the lens formula. So this is what we observe. So as you decrease the value of x from focal position towards origin, your image also goes from infinity to the origin. But remember, you're viewing the image with your eye, so you can't let it come that close actually. You are under the constraint that the image that you're seeing should be within your near point. So y should be less than equal to capital D. Okay, so if you keep the object nearly at the focal position, the image is very far away. So your eye is comfortable, but you are achieving a magnification of this much. And we'll see this is the minimum magnification. Because as you bring the object closer and closer, the magnification increases. But how close can you bring it? That is the point. Okay. So now, the second thing is, if x is brought to the minimum value, then the corresponding value of y is d, because y cannot come closer than d. So this is the position where our angular magnification will be maximum, because the image is as close as possible. So in this, what is happening? The image is at the near point. So this is called the near field adjustment. That was called the normal adjustment because the image was very far away. This is a near field adjustment. So in this adjustment, always your magnification is maximum and the image is at the near point of the eye. That is, the image distance is equal to capital D. Okay, so this is a general thing you should remember for all optical instruments. So यहाँ पे क्या हो रहा है? Let's see. So we have 1 by x minus 1 by y is equal to 1 by f. So in this we are putting the value of y as capital D. So x is becoming x minimum. So on substituting, you will see that x minimum becomes df upon d plus f. Okay. And now you substitute that in angular magnification formula, which is d by x. So here it becomes d by x minimum. So when you substitute this value here, you get the angular magnification as 1 plus d by f. So this is the maximum possible magnification. And this occurs for the near field adjustment position. And in this, the eye is highly strained. So y is equal to capital D. That means the image is at the near point. So in viewing it, there is maximum strain on the eye. But on the other hand, the magnification is also maximum. Yeah, sure. I'll show the normal adjustment again. So this general principle of normal adjustment and near field adjustment, you should remember, is common to all optical instruments. Normal adjustment में क्या करते हैं? We keep the position adjustment such that the image is very far away, so our eye is very comfortable. But comparatively, the magnification it achieves is less. Whereas in near field adjustment, we adjust the value of everything such that the image is at the near point of the eye. So it is closest to the eye as possible, which is capital D. So in that position, our eye is under maximum strain, but at the same time, the magnification we achieve is maximum because the image you are seeing is closest to you possible. Okay. So now you come to the near field adjustment position. This. Okay, people, so this is how we get the final formula for near field adjustment. So you can see normal adjustment was just d by f. This is d by f plus 1. So the magnification factor is increased by 1. So your range of magnification becomes like this. This is near field. This is normal adjustment. Alright, so as I was telling you, once you understand this, the other type of optical instruments are comparatively easy to understand. So for example, the one which is there in detail in your syllabus is the compound microscope. So this uses a combination of two lenses called the objective lens and the eyepiece. So objective lens has focal length FO, eyepiece has focal length FE. Both convex lenses. To achieve angular magnification, large value of angular magnification. So the typical structure is like this, that so the observer looks straight into the lens called the eyepiece. So when you use a compound microscope in a lab, like a bio lab or something, to observe things like cells or amoeba or things like that, you put your eye right against the eyepiece. So that lens is called the eyepiece. It has a focal length of Fe, and your object is kept somewhere near the other lens on the other side. That is why that is called the objective, because it looks into the object. It's called the objective lens. Now, if the object at a distance x1, let's say, focus from this thing, it is full. So x1 is usually taken to be greater than f of the objective, but less than. So the objective lens produces A. Now remember, if this is between f and 2f on this side, it produces a magnified but inverted real image, okay, of AB. Let's say A prime B prime, which I'm drawing over. So same. So this is producing your inverted but magnified real image, E prime B prime, of height h prime, let's say, where this is h. So let us say the image is now at a distance of y1. So we have that relation that 1 by x1 minus, in this case हो जाएगा plus 1 by y1 will be equal to 1 upon FO, because we have substituted U as minus x1, V as plus y1, and h prime upon h will be the linear magnification, which will be nothing but y1 by x1. So this is what the objective lens is. Now what happens, this image produced by the objective lens, that becomes the object for the eyepiece. So if this image is at a distance of x from the eyepiece, again we adjust the distance between the two lenses such that x is less than f. So ये जो object बन जा रहा है इसलिए a prime b prime, that is closer than the focal point, so it produces an image behind it. So next thing is this image produced by the eyepiece, sorry, by the objective, E prime B prime, is now the object for the eyepiece. Now you adjust it such that at x, such that x is less than the focal length of the eyepiece. So now the eyepiece produces a virtual inverted magnified image of A prime B prime, and that becomes the final image, let's say A double prime B double prime, as seen by the viewer E on the other side. Okay, so now let's imagine some rays like this. Now these rays they behave such that when produced back, and here let's say they produce the image. So my final image actually becomes this, which is A double prime. So the final image is subtending this angle theta at the position of the eye. So that becomes the angular size. So the final image is now at this kind of distance y from this. Okay. So for the objective lens, we have 1 by y, so 1 by x minus 1 by y equal to 1 upon fe for the eyepiece. Okay, because our u is minus x and our v is also minus y, because it is a this thing. This image is virtual and upright. And the angular size theta, which is basically A double prime B double prime upon y, is also A prime B prime upon x, which is basically h prime by x. And h prime was nothing but the linear magnification produced by the objective into h divided by x. Okay. So this is because h prime was m times h, where m was y1 by x1, or linear magnification by objective. Okay. So this becomes the formula for angular size theta. So therefore angular magnification becomes theta upon theta naught, which here is mh by x divided by h by d, which is the maximum angular size you can see without any optical instrument. So the formula of angular magnification is very similar to the formula that we got in the case of the simple handheld lens. It is multiplied by this factor of m, something like this. So it's one linear factor of magnification, which is obviously greater than 1, multiplied by this. So this is the angular magnification. Again, we can see the conditions that we can apply on x for near field adjustment and normal adjustment, and that will give us the range of magnification that we can achieve using this instrument. Okay. So I'll just give you a bit of time to go through this and understand this properly. Okay, people. So this becomes the effect of the. Okay, so now this image produced by the objective lens A prime B prime, that becomes actually this thing, and becomes the object for the eyepiece. Okay, so okay, what happened? So you apply the lens formula for the eyepiece. Okay. So you get this kind of relation between. So here again you will get that same relation between x and y. That x is equal to dy upon d plus y. If you'd seen earlier for the handheld lens also. But because there's one stage of magnification happening before you come to the objective lens, so before you come to the eyepiece. Okay. So there's this. There's m multiplied by d by x. Okay, now we come to the different type of adjustments. So you can see that for range of magnification, if we keep x almost at the focal position, it's slightly less, then the image is very distant. Okay, this is the position of E double prime, B double prime. So it will be what we call the normal adjustment position. Which is basically minimum magnification, but comfortable for the eye. Okay, so it's comfortable to view. Whereas on the other hand, if you put x to the minimum possible value, y is the minimum possible value, which is capital D. Okay. So this is when the image A double prime, B double prime is at near point of the eye. That is called the near field adjustment. At which basically what happens is that the magnification is maximum, but the eye is under maximum strain also. Okay. So anyway, so let's see both of these cases separately now. So for near field, for normal, so normal adjustment में क्या हो रहा था, x is equal to focal length of the eyepiece. Okay, so the angular magnification, which is m into d by x, becomes m into d by focal length of the eyepiece. So this is the minimum magnification, minimum value of angular magnification. And for near field adjustment, x is equal to x minimum, so that y becomes d. So now using that lens formula that we'd seen earlier, this x minimum actually becomes dfe upon d plus f. Okay, because we had the formula 1 by x minus 1 by y is equal to 1 upon fe. So from this formula, put this here. So from this now you put the angular magnification is m times d upon x minimum. So you get the angular magnification as linear magnification produced by the objective into 1 plus d by f. So you see how the formula is symmetric. Just this extra factor of m multiplied comes in. Okay, so this is the maximum. So overall you can see for the lens, the angular magnification is in this range, m into 1 plus d by fe, which is the near field adjustment, where x is equal to x minimum and y, the final position, is at near point of the eye. And on the other hand, the minimum magnification that you can see is m into d by fe, where this is the normal adjustment, where x is equal to fe and y is infinity, or basically a large distance. So this is the range of magnification. And in this, of course, remember that m is a linear magnification produced by the objective. So that M is nothing but the size, linear size of the image of the objective iris, which was nothing but y1 by x1 in our original diagram. So this is the entire explanation of the compound microscope, which is basically the important optical instrument that you have in your syllabus for direct formula type of questions. Yeah, so from this point, range of magnification. Let's take a look at it. Okay, so people, hope you've understood this. Okay. Okay, so this is the final part of this, guys. Okay. So that's it for today's class, people. Next time we'll briefly discuss about the astronomical telescope, but that is also based very much on these principles. And then we'll come to combination of lenses and lens with mirror type of problems, which will be like your more typical JEE advanced type of question. Okay? So that will then complete off geometrical optics. Okay, so that's it for today's lecture.